Hi everyone. So welcome back. Let's start from where we left off. So we had started with this idea that we want to estimate the parameters, and we reintroduced the concept of error. And what we understood is that in our random guess algorithm or the guesswork algorithm, right, we were actually navigating the error surface, although we were not realizing we're just moving from here and there. And at times we were making a mistake where we went up the error surface, right, or went to a higher error. And we don't want that to happen, right? We want a journey which is smooth, that you keep going down as far as the error is concerned, and then settle to a point where the error is minimum, right, if not zero. So we need a more principled approach, and that's what we are going to do in this module, right? So this is the goal, as I just stated, that find a way of traversing this error surface so that we can reach the minimum quickly and without a lot of backtracing or like going back, or not backtracing actually, but random jumps here and there, which don't necessarily decrease the error at each iteration, right? And we don't want to do this brute force search either, right? So that is not possible, right? We cannot plug in all the values of the parameters and then see that value which gives us the minimum value. That would be the brute force search. We cannot do that, and we have argued why that is infeasible. There are infinite values there. Okay. So let's look at the setup now, right? So we have our parameters in the toy network were w comma b. I'm just going to put them in an array or a vector and call that vector as theta, right? So now theta is my parameter of vectors, and now I'm looking for changing this value, right? So just as is always the case, I don't know what the correct theta is. So I'm going to start off with some random value for theta. And when I start off with this random value of theta, I want to know how much to change it so that at this step at least, I'm looking at it one step at a time, at this step at least, the error should decrease, right? So I'm looking for that change in theta, which is nothing but a change in w and a change in b, so that I get a new value of theta, and then my loss has hopefully decreased. I'm not sure of that yet, but that's what the goal is, right? So this is my theta, some vector. Delta theta is also a vector, right? It's also a vector in R2. This is a vector in R2. And similarly, this is also a vector in R2, right? Now, these are two vectors. Now, what I'm going to do is my change is going to be just given as theta new is equal to wherever I am currently, I'll move by this change, right? So theta new is equal to theta plus delta theta, okay? So what is happening here is that I was here, and this is where I was, and I then added this vector, and what has happened effectively that I moved in the direction of delta theta, right? I've come closer to delta theta, and we know this from the perceptron learning algorithm also. When we add it, it comes closer to it, right? So now instead of moving fully, so let me just delete this, right? So instead of moving fully in the direction of delta theta, what I'm going to do is I'm going to be a bit conservative, and whatever change you tell me to do, I'm not going to do that full change. I'm just going to multiply that change by a very small value, which is eta. So essentially what that does is the following, right? So this is my delta theta vector, the black one. I am going to multiply it by a small scalar. So essentially the magnitude of the vector will decrease. The direction does not change. So I'm still going to move in that direction, but I'm just going to be a bit conservative and take a small step, right? One small step at a time, right? So that gives me my update rule, which is if you tell me what is delta theta, then I'm going to move by a small value in that direction, right? That's what my update rule is going to be. Now the question of course is, what is the right delta theta to use, right? I was earlier, what was my algorithm in the random guess? I was just coming up with some delta theta, just moving there, and then realizing, the error has decreased. So let me just go back and then try to find some new delta theta, change that, and change that much, and then find a new value. I don't want to do that. Someone has to give me the right delta theta to use. And it turns out that what is the right delta theta to use, the answer from this comes from the Taylor series, right? So let's see first what is Taylor series. I'm sure some of you have seen this in high school, but let's quickly refresh this, right? So Taylor series, as I'm just going to read out the definition here, is a way of approximating any continuously differentiable function, right? And this is important for us because whatever loss function we are dealing with is a differentiable function, because We have the sigmoid neuron, which is differentiable, and then on top of that, our loss function currently is the squared error loss, which is again differentiable, right? So this is a differentiable function that we are dealing with, and this differentiable function may have any shape, right? It could have a shape like this. It could have any shape. It's just smooth and differentiable, right? And what Taylor series does is it gives us a way of approximating this using polynomials of degree n, right? And the higher the degree, the better the approximation. Now this part may not be clear, right? What do I mean by approximate using polynomials of degree n? I should have circled n also. That part is not clear and we will fix that, right? Let's try to understand what we mean by that, okay? So I'll delete some of this. Okay, so here's a function, right? So let's assume this is my w. I have a single parameter for ease of explanation, and this is my loss function, right? This is L of w, suppose, okay? And what it's saying is that as w increases, L seems to increase, right? So that's okay. Whatever this function is, I don't care about it, but this is how the function looks like, okay? Now suppose there is a point w naught, okay, at which I know the loss, okay? And where is this coming from? How does this relate to our original, our goal, right, which is to find a new value of w such that the loss is less, right? So that will soon get related, but for now I'll give you some intuition, right? So suppose there was only one parameter and I timed step 0, I started with the value w naught and I could compute the loss. I don't know the full loss surface, but I could compute the loss, right? Now I'm looking to change this value w naught, right? And I want to decide whether to go here or here so that my loss decreases. That's what the goal is, and we'll relate all of this discussion to that goal soon, right? In the figure, it's clear that I should move to the left because there is where the loss is decreasing, right? But that's what we are trying to do. So now if I know this w naught, what the Taylor series does is that if I know a point w, okay, which is w naught plus some delta, okay, if that is the point, right? So then delta is equal to w minus w naught, right? And you see that w minus w naught quantity everywhere here, right? So if I know the value of the loss at a certain point, then I can approximate the value of the function in a neighborhood around that. What do I mean by that? This w, if this delta is very small, then w lies in the neighborhood of w naught, right? So in that neighborhood, I can approximate it by using this formula, right? And the interesting thing about this formula is that it has this first order term, it has a second order term, third order term, and so on. And I can cut off the formula wherever I want. If I cut off the formula here, I'm doing a second order approximation. If I cut off the formula here, I'm doing a first order or a linear approximation. So let's see what happens when I do a linear approximation, okay? So I'll again delete stuff on the slide. So this is what the formula looks like. I've just cut off the formula at the first order terms, right? So I just have this much, okay? And now I want to find the value of w, and I'm saying that I already know this, right? I already know what Lw naught is, right? That is given to me. Now I'm saying that Lw is just going to be this. Lw is just going to be this, which is whatever was my current value plus some quantity, okay? And what is this quantity? This is L dash w naught. L dash w naught is nothing but the first order derivative of the loss function. W minus w naught is actually the delta between that, right? Now, what is happening here? All this looks very confusing to me. So let's just try to draw a line here. So what am I doing here, right? The actual function has a curve, right? It's definitely not a linear function, right? But I'm approximating that function by a linear function. I'm saying that in this small neighborhood here, right? Say from, this is the small neighborhood. In this small neighborhood, I'm going to assume that the function is linear, right? Now, if the function is linear, that means I have assumed that the function is of the form y is equal to mx plus c, okay? And I already know y naught, which is mx naught plus c, right? I already know that, right? And what is m? M is simply the slope, and the slope is just the derivative, right? So this is L dash w, right? So this is what the slope is, right? Now I want to find the value of y1, right? And I know that say y1, let's just see, right? So y1 would be m into x1 plus c, right? Now if I subtract these two, if I subtract the first equation from the second equation, I get y1 minus y naught, okay, is equal to, the c's will cancel and you will have m into x1 minus x naught, okay. And if I rewrite this, I'll have y1 is equal to y naught, okay, plus m into x1 minus x naught, right? And that is exactly what this formula is saying, right? So y naught is nothing but LW naught, m is the slope, and w minus w naught is the same as x1 minus x naught, right? So that's what it's saying, that now you can find y1 by assuming that this is a linear function, okay, and then you know the slope because you can compute the derivative at that point, and now I can get a new value for y. I can get the value for y1, where y1 is the value of the function at the point x1, and there is a small delta between x1 minus x0. That means x1 lies in the neighborhood of x0. Okay, and it will soon become clear why this is important. Okay, so everything that needs to be explained has not been explained on this slide yet. I still have some visuals on the next two slides which will make things more clear, right? But let's just go ahead with what we have now, right? Let's just try to understand what it means to have a linear approximation. You're just drawing a line at that point, right? And you're saying that if I just move along this line, right? So instead of moving along this curve, which is what you should have done, you're moving along that line, and whatever value you get on that line, that is the value you're assuming for y1, right? So that's an approximation, and you can already see, right, that this value here, let me just mark it with a different color, right? So this blue value here is what you would get, right? That's the point on the line. It's slightly above the red curve, right? So it's an approximation. You will get some error there because you've done a linear approximation, right? Now let me just get rid of all this content. And now let's see if I had done a quadratic approximation. That means if I had cut the formula here, right? So what happens in that case? This is what the formula looks like, right? And just as the first one was of the form y is equal to mx plus c, right? And here you have a quadratic term. So this is nothing but y is equal to ax square plus bx plus c, right? So now I am approximating the function as a quadratic function, right? And these coefficients are coming from the derivatives, as was the case in the first case, the first order derivative, the second order derivative, right? So what does that mean? It means that now I'm approximating the red curve by this cyan or blue colored curve, right? And you can see that in the small neighborhood now, right? This neighborhood now, the second order approximation is actually better than the first order approximation, right? It's more closer. The blue curve in that small neighborhood is more closer to the red curve than the black curve is to the red curve, right? So this is, you can just keep cutting the formula wherever you want, and that's what the approximation gives. How this relates to what we are trying to do, all that is not clear right now. Right now we just want to understand what Taylor series is. Taylor series just gives a way of approximating the function, and we can use any order of approximation, n equal to 1, n equal to 2, n equal to 3. The higher the order, the better the approximation. Okay, so now let's kind of move ahead from here and see where to go. Yeah, so now here's the same plot, right? And now I'll do some stuff here. So this epsilon actually defines the neighborhood. Oops. Right. So the smaller the value of epsilon, you can see that the smaller is the neighborhood that I'm considering here. Okay, and I'll tell you why that is important. Okay, now this function is log of w. Okay, and now I know the value of the function at this point here. Right, this point here, I'm going to approximate its value in the small neighborhood around it, right? And the value would be whatever is on the orange line, because that's the linear approximation I have made. That's the line that I have drawn, and I'm trying to approximate the blue curve by this line. Now when the epsilon is small, that means when I'm looking at a very small neighborhood, this orange line acts as a good approximation of the blue curve, right? In that small neighborhood that you see between these 2 points here, that is the orange line is very close to the blue line. But as the neighborhood increases, right, if you go very far from the point that you were, and now you are going to try it. So this is your x naught, right? This point here is your x naught, right? And let me consider some x1 here, right? So now this should have been x1. So now what it is telling me is that if I try to compute y1 is equal to y naught, right? So this point here on the line is y naught, okay? If I try to compute y1 is equal to y naught plus the formula that I had, right? M into x1 minus x naught, right? Then the answer that I'll get is this. And you can see that it's way off, right? It's not really a good approximation. Even if my x1 was here, right? And then what I'll get, if I substitute in this formula, I'll get the y1 as this point. And you can see that it's actually very far off from the true value of y1, right? So hence this, as the neighborhood grows, this approximation becomes bad. So that is a key thing, that you can do this only in a small neighborhood. That means the difference between x1 and x0 should be very small. That is one, okay. Now let's see something else also. The other thing is that as I increase W naught, right, I mean, I'm just changing the value of W naught, and you can see that the orange curve is a very good approximation. Oops. Let me just increase the delta a bit. Let me reset this. Yeah. Now I'm just going to increase the neighborhood, right? Okay. Now even with this increase in neighborhood, the orange line still seems to be a very good approximation of the blue curve. And why is that happening? Because the slope in that region, right, is quite less. So my delta or my m, right, it's very less, and that's helping, right? But now if I change the value of w a bit, right, if I go here, now here my slope is very high, as you can see, right? The gradient is very high, and now in that case, my approximation is becoming very bad, right? So this is what the same window, I have not changed the window, right? But now if you can see, this is the approximation and this is the true value, and the gap is very high, right? Whereas with the same window, if I am in a region where the slope is small, right, then still the approximation is quite good. You can see that the points on the orange line are very close to the points on the blue line, because this is a region where the slope is very low, right? Whereas this was a region where the slope was very high, right? That's just some observation. So now you can see what is actually happening in the Taylor series approximation. Wherever you are, you're drawing a tangent and you're saying that this line given by the tangent is my approximation for the original function. And in small windows, that approximation works very well, right? Even when the gradient is large, right? So if my window is small, oops, then even as my gradient changes, right, my approximation is still quite good, right? So in the small neighborhoods, my approximation always remains quite good, even for high values of the gradient. But if my my window is large, then the approximation becomes quite bad, as you can see here, right? So that's important, that Taylor series is only used in small windows, okay? Now that was one. Now let me just reset this, okay? And I change the function, okay? I want to make it the sine function, okay? And now this is what my approximation looks like. Now I'm going to increase the degree. So this is a linear approximation right now, right? Because I've just cut off the formula at the first order term. Now this is a quadratic approximation. You can see that it looks better, right? The orange curve is closer to the blue curve, right? And now what I'm trying to prove actually is the utility of the Taylor series, or how good the approximations get as you keep increasing the degree. So this is a degree 2 approximation where I cut the formula at the second order terms. If I cut the formula at the third order terms, this is what I get, right? And now you can see that in a very larger neighborhood also, right, the approximation is quite good, right? I mean, the true curve is very close to the orange curve, right? Let's increase it further. further, further. I think I'm at degree 7 or degree 8 now, and it's almost perfectly approximating it, right? So as I keep increasing the degree, the approximation becomes better than that. And if I go till the very large terms, then I'm constructing the entire function in by as a sum of its parts, right? And that's what the Taylor series actually says, that if you use the full formula, then you get the function back, right? That's the beauty of the Taylor series approximation. If I keep decreasing, then my approximations become bad. And in the linear case, my approximations are bad, but they are very good in a small neighborhood around the point, right? That's the main, yeah, in the small neighborhood, yeah, my approximations are quite good, right? So that's the main thing you need to understand about the Taylor series. Okay, so now let's go ahead and see what happens if you have a 2D function, right? So I had earlier, now I was just dealing with L of W. Now what if I have L of W comma B, right? And in this case, instead of W comma B, I just have X comma Y, right? For convenience, those are the two axes that I have taken. Okay, but the main point is if you want to move to two variables, right? So now, oops. Yeah. So this is what the curve looks like, okay? And let me just delete my annotations. Yeah. So this is what the curve looks like. Now again, if I do a linear approximation, as you can see here, I'm doing a linear approximation, then what I'll get is a line in 2D, which would just be a plane, right? So I've just approximated the function by a plane, and you can see that in this small neighborhood, my approximation is still good, right? Let me just get the right angle so that you can see it properly. Yeah, see. Now I can see that my plane is very close to the curve, but now if I increase this eta, right, then as was the case earlier, my approximation becomes bad, right? So at this point, my approximation, if my original point W naught was here, then if my new point is very far out of the neighborhood, then the approximation would be bad. But even in the small neighborhood, the linear approximation works quite well, right? And again, I could just change the value of X. And if I go to a region where the slope is changing, then the approximation accordingly will become good or bad. But that doesn't matter. If you keep the eta small, then your approximations would be good, right? And now if I make a quadratic approximation, right, I'll just remove the linear one and just keep the quadratic approximation. I think you're not able to see it. Yeah, so here's the quadratic approximation, right? And now even if I increase the the window a bit, you can see that my approximation is still quite good, right? So that's the idea here. In fact, the original function itself is quadratic in various parts, right? So that's why my approximation is quite good, right? So that's the idea here. So the original function is of course 0.5 sin x plus 0.25 sin y, but what I meant it in some parts it's it's looking like quadratic function, right? So if you do a quadratic approximation, it still would be very good, right? So you can do this whether you have a one variable function or a two variable function. Of course, three variable functions I cannot. I'm just trying to get the angle right. Yeah, this is what it is, and you can see that the approximation is good. So this is what the Taylor series does, and you can do this approximation in multiple dimensions also, right? So it need not be a function of a single variable. It can also be a function of multiple variables. Okay. So I can take a pause here. I'll let you reflect on this. You could also go back to the lecture slides, right? The slides are also available on my webpage, and you can just go and try to play around with this, digest this idea, and then come back and watch the next video. Okay, I'll just take a pause here. Thank you.